So our next topic is going to be the topic of what is a basis for a vector space and what is a dimension of a vector space. But before that, we need a little preparation in the sense that we need to figure out some things that relate to a set of vectors. When is that set of vectors, when does it generate the entire space? So, and when is it the optimal set that generates the entire space? So those notions relate to linear independence or dependence into spans, but we want to make to observe some specific issues more delicately. So the first question that we want to ask: suppose we have two sets of vectors. So we look at v1, v2, up to vk. So here's a set of k vectors in some vector space. And we look at their span. So the span is all the possible linear combinations of these k vectors in the spanning set. And suppose we have another set, let's call them w's, w1, w2, all the way up to wm, not necessarily the same number of vectors, and we look at this at the span of these w's. And the question that we want to ask: when are these two, this is a vector space generated, or a subspace of the bigger space we live in, generated by w1 through wm, this one's generated by v1 to vk, and we're asking, when are they the same? What can we say about these sets being equal? Are they equal? Well, of course not necessarily. When are they equal? And the statement is going to be that these two are equal. So this is going to be a theorem, in fact. These two vector spaces are equal if and only if each of the vi's is a linear combination of the wi's, and each of the wi's is a linear combination of the vi's. Okay, so let's write that. If and only if every vi is a linear combination of the wj's, and every wj is a linear combination of the vi's. It may seem at first glance like a completely trivial statement, but there's something, it's not a hard theorem, but there's something non-trivial here. So let's see what it is. So first of all, do you see that there are two things that we need to prove? We need to prove that if the spans are equal, then every vi is a linear combination of the wj's, and the same for the wj's. So there are two directions. The first direction is going to be, so prove, the first direction, this direction. Suppose we know that the two sets are the same, the two vector spaces are the same, well, then it is trivial. Because, let's look at the statement again, if this vector space equals this vector space, then every element here, in particular each one of those vi's, which are elements here, can be written as linear combinations of the sets that generate this vector space. That's the meaning of a spanning set. Do you agree? And vice versa. So do you agree that the direction spans are equal implies every vi and so forth is indeed trivial, follows by the definition of what is a span? Okay? Okay, so this direction is straightforward. By the definition. I'm not going to spell out all the details and just say the words again and again. Okay, good? What's not entirely trivial is the other direction, and let's understand why. So suppose that we know, let's go back to the statement, suppose that we know that every vi is a linear combination of the wj's. that doesn't mean that the span of the VI's, that any vector here is a linear combination of the WJ's. We need to show that. Okay? So in this space, there are more vectors than just the VI's, right? Any linear combination of the VI's is also here. So let's take an element here, let's call it V. What we need to show is that V is a linear combination of the WI's, and not just the VI's. So that's the little extra detail that's not explicitly written here and requires proving. Okay, so let's write that. Take V in the span of the VI's. Any vector here, not necessarily one of these. We need to show that V is a linear combination of the WI's and vice versa. Okay? Then we know that V is a linear combination of these guys. That's what it means to belong to their span. So we know that V can be written as sum I equals 1 through k of alpha I V I. That's what it means that V is a linear combination of those guys, right? Yeah. Now we know that every VI is a linear combination of the WJ's, because that's what that's the given in this direction, right? So we can rewrite this as sigma I equals 1 through k alpha I, and now instead of VI, I'm going to write sigma j equals 1 through m beta j wj. And I have to be a little more careful, so I replaced here VI by a linear combination of the WJ's, but I have to indicate that this is the linear combination for VI, right? So I'm going to call these coefficients beta ij. I because it's the coefficient in writing VI as a linear combination, and j because that's the index of this summation. Okay?
I didn't get the last part. Why did you have to mention that?
So how do you know that this, if this I weren't here, how would you know that this is VI? What makes it VI and not...
It's a linear combination of...
No, but here there's V2, V3, V4, V5. How do you know that this corresponds to V3? What makes it V3 and not V4? I have to indicate somehow that this is V3. When I is 3, this is the linear combination for V3. Good? Clear? Sure? Okay. And now I can rewrite this. These are finite sums. So I can rewrite this as the sum j equals 1 through m of... how do I want to write it? I want to take all the coefficients inside. So sigma I equals 1 through k alpha I beta ij wj. And now V is written as a linear combination where these are the coefficients of the WJ's. Okay? So every general vector in this span is a linear combination of the WJ's. And likewise, every W is a linear combination of the V's. And therefore, the spans are indeed the same. Okay? So it follows, or let's not use this because it's confusing with this. So therefore, every V is a linear linear combination of WJ's. And likewise, every W is a linear combination of VI's. Good? So is it clear why we needed to say this and why it wasn't just automatic from the fact that each VI is a linear combination of the WJs. We need to say a bit more. Okay? Good.
Mathematically move the beta from the sigma m to the sigma k. How does that work?
Well, if the sigma notation is confusing, what you need to do is open it up. Spell it all out, right? Alpha 1, so here you would what? Alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3. And then for each V, you would replace it by this sum and spell it out completely. And then see what you can do. Okay, I'm only using basic properties of being a field, that you can commute things and you can associate things. And okay, but if the sigma notation is what's confusing, then you have to just look it over when you open everything up, and then things become clearer until you get used to the sigma notation. Okay? Okay, so what I want to write now is corollary. I never remember if there are two R's or two L's or two C's. Nah. Two L's, like this, right? Corollary. So it follows from that theorem that if we look at the span of V1, V2, up to Vk, and we ask, what would happen if we added one more guy, one more element? So V1, V2, Vk, and now we throw in somebody new, W. How could we characterize when these two spans are the same? When did W not add anything?
If the W is a linear.
Right. So if and only if, W is a linear combination of the VI's. Why is this a corollary? Why does it follow automatically from the previous theorem? Because, so there are two directions again. If the spans are equal, then by the previous theorem, every element in the spanning set here is a linear combination of these guys, and vice versa. Obviously, every VI here is a linear combination of these guys, because they're just all there. The only new information that we have to show is that W is a linear combination of these guys, and by the previous theorem. If they're equal, then each of these are, and in particular, W is a linear combination of the VI's, right? So that's this direction. The spans being equal when you added one more implies that the one more that you added was already a linear combination of those guys, okay? The other direction, if you know that W is a linear combination of the VI's, okay, and obviously all the other guys are linear combinations one of the other because they're the same on each side, then you know the other direction of the previous theorem, right? You know that each element here is a linear combination of these, and each element here is a linear combination of these, and therefore the spans are equal by the previous theorem. Okay? So is it clear that this is a direct corollary? Okay? Now, the way to think of this corollary is not as something very abstract. You should have a feeling for this. You should have intuition for this. What this corollary says is the following. You take V1 to Vk, you take a spanning set, you take a set of elements and look at what they generate in terms of linear combination. You throw in one more guy, and you're asking, can we generate something new? Did he add any information, or was everything already here? And the answer is, the intuitive answer is, well, if W itself was already generated by the VI's, then he can't add anything new. And if he wasn't, then obviously he can, for example, himself. Okay, clear? That's the intuitive approach to this. Okay, so here's another theorem along these same lines. Let the set V1, V2 through Vk be linearly independent. Linearly independent. Okay? And we're asking the same question. What happens if we throw in one more guy, W? Then the set V1, V2, vk w is linearly independent if and only if, what would be your guess?
It's not a
Right, if W is not a linear combination of the VIs. If and only if W is not a linear combination of the VIs. So before we prove this, okay, I want to make a remark. I assumed here that the set that we started with was linearly independent. Because otherwise, we already know the answer, right? If the set is already linearly dependent, and we add something, it's still going to be linearly dependent. That's the theorem that we had last time, right? If you take a subset, if you take a set that includes a linearly dependent set, then the bigger set is already linearly dependent, okay? So if you add something to a set that's already linearly dependent, it's automatically linearly dependent. The question is, when can you add something to a linearly independent set and still keep that linearly independence? In other words, now we're not asking if we can add anything new, we're asking if anybody is extra, right? That's the notion of linearly independence. So we're asking, we throw in one more guy, is he extra? Did we really need him? Does he add new information in that sense? And the answer is only if he's not a linear combination of these guys. Okay? So let's prove this. Let's look at a new board. So proof. So again, we have two directions. Let's look at this direction first. So assume that V1 through Vk with W is linearly independent. Show that W is not a linear combination of the VIs. If V1, V2 through Vk and W is linearly independent, then nobody here is a linear combination of the others, right? And in particular, not W. Do you agree? Then, right, because being linearly independent implies that if you take any linear combination of these and you get 0, then all the coefficients were 0, right? That was the definition. So if W were a linear combination of the VIs, you would move W to the other side and get a non-trivial linear combination that's 0. Do you agree? Okay. So if the set is linearly independent, then by definition, or let's write then, no VI or W, yeah, then no element, no vector in this spanning set, no vector in this set is a linear combination of the others. And in particular, not W. Okay, good? And again, if you want to go one step back to the definition, you would say, assume that W is a linear combination of the others, write W as a linear combination of the others, move W to the other side, from suppose you wrote W equals the sum of the alpha I VI, subtract W from both sides, you get W with a coefficient of 1, so you get a non-trivial linear combination of all of these that equals to 0. Okay, and that cannot happen in a linearly independent set by definition. Good, everybody? Okay, other direction. So suppose we know that W is not a linear combination of the VIs. We need to show that this set is linearly independent. Okay, so now I'm gonna use a bit of logic here. So let's look at this board a minute. I want to show this direction from here to here. If W is not a linear combination, then this set is linearly independent, right? Logic, when you have a statement A implies B, that's equivalent. It's the same thing as saying not B implies not A. Do you agree? So proving this implies this is equivalent to proving that if V1 through Vk plus W is not linearly independent, meaning is linearly dependent, then W is a linear combination of the VI's. Do you agree that that's exactly the same statement? Okay, so let me write that. We will show that if V1 through Vk together with W is linearly dependent, so not linearly independent, then W is a linear combination of the VI's. So does everybody agree that showing this is precisely equivalent to showing this direction of that theorem? Okay? And now I'm going to rely on a previous theorem that we had. So when we have a set that's linearly dependent, a previous theorem that we had said that, well, one of them is a linear combination of the others, but in fact, we even had a statement that one of them is a linear combination of the ones that preceded him. Remember that statement? Now, the assumption of this whole theorem is that without W, it's a linearly independent set. So the VI's cannot be a linear combination. None of the VI's can be a linear combination of the ones that preceded it, because that would mean that the VI's are not an independent set. Right? So the only one that has the possibility of being a linear combination of the ones that preceded it is poor old W. Do you agree? So let me write that. By a previous theorem from one of the previous lessons, by a previous theorem, there exists a vector which is in this set, which is a linear combination of those that preceded. Its predecessors, what we call. What? Good? So the only one that can be that is W. So since V1 through Vk without W is linearly independent, that's the data of the theorem, that vector can only be W. So W is a linear combination of the ones that precede it. Okay? Good, everybody? Okay. So this completes this statement. So now we know a bit more on what happens when you have a given set. Maybe let's look again at this board. What happens when you have a given set and you add another vector? Okay? So what does that vector have to satisfy in order for the new set to still maintain the property of being linearly independent? And what does that vector have to satisfy in order for the bigger set to still have the same span? So that's these two statements, and we're going to quote them and rely on them when we define a basis and study bases vector spaces. Before I end this lesson, I want to just write one more theorem, which uses these facts. It's not directly related to the facts themselves, but it uses them, and it's important for our discussion of the relation between matrices and systems of equations and all these notions of spanning and linear independence and etc. in a vector space. So here's the theorem, or maybe let's write a reminder first. Reminder. So we denoted by rho of A, where A is some matrix, the vector space spanned by the rows of that matrix. Remember that? So this is by definition the span of the rows of A. Okay, remember this definition? We also had a definition, call A is the span of the columns of A. Okay, but I'm going to relate to this one right now. So here's the theorem that I want to mention. A and B, two matrices, A and B, are row equivalent. Remember what row equivalent means? That you can transform one into the other by a finite sequence of elementary row operations, interchanging two rows or adding a scalar multiple of one row to the other, etc. Remember? Okay, so two matrices are row equivalent implies that they're the span of the rows, the row of A, equals the row of B. So the rows span the same subspace. Okay? And I'm not going to write a fully detailed proof. I'm just going to give you the idea, and the idea is everything. I'm not hiding anything sophisticated or not even technical. I'm just, in order to save time, I'm just going to give you the idea, and you can fill in the details if you wish later. But what I want to remark is that, in fact, this is an if and only if statement, but the other direction is complicated. Okay, and I'm not going to prove it. So I'm just going to remark it. So remark the converse also holds. Okay, so if two matrices have the same row space, then they're row equivalent. Okay, so let's give the idea of the proof of this theorem. So idea, let's write it on a new board. So try, while I'm erasing this board, try thinking, why would a statement like this be true? What do you need to show? Honestly, this direction, if you understand, if you decipher what you need to show, then you showed it. Okay? Understanding what you need to show is really everything here. So let's figure it out. So we want to show that they have the same row space. Okay? So what does it mean? By the theorem that we just erased, when our two, this is the space generated by the rows of A. This is the space generated by the rows of B, the span of the rows of B. Okay? When is the span equal a different span? If and only if, by the previous theorem, every row here is a linear combination of the rows here, and every row here is a linear combination of the rows here. Do you agree? Okay? So, and everything here is symmetric, so without loss of generality, I can just show that every row of A is a linear combination of the rows of B. Do you agree to that? Okay? So let's first write that. So, outline outline of proof. By the previous theorem, it's not the previous because we had one after it, by a previous theorem from a couple of minutes ago, it suffices to show that each row of A is a linear combination of the rows of, let's show that each row of B is a linear combination of the rows of A. Okay, in some sense it makes things more natural, but it's of course completely symmetric. Do you agree that this would prove it? Okay, so what do we know? We know that they're row equivalent. So we know that there was somehow, so since A is row equivalent to B, let's not. Since A and B are row equivalent, we know that there was a finite sequence of elementary row operations where we started from A, did one operation, got to another matrix, let's call it A1, and then we did another operation and got to A2, and then we did another row operation. Each step is only elementary row operations, and eventually we got to B. That's what it means that they're row equivalent. Do you agree? Okay. So I want to show that every row of B is a linear combination of rows of A. Do you agree that if I show that every row of A2 is a linear combination of the rows of A1, that would suffice? Well, in general, if I showed that any row of AI is a linear combination of the rows of AI minus 1, that would suffice. That would mean that in each step, the rows were linear combinations of the rows of the previous step, and therefore you can even formalize it to say, by induction, the rows of B are linear combinations of the rows of A. Do you agree? So it suffices. So since A and B are row equivalent, we have this sequence of elementary row operations. It suffices to show that every row of AI is a linear combination of rows of AI minus 1, where B is the last step. Let's call it a n. Okay, so let's assume that there are n steps. Do you agree that this would prove it? Okay? And now we're done. Right? We deciphered what we need to show, but okay, now we need to show it. We keep saying it suffices to show, but that's it, we're done. Because what is an elementary row operation? So what is a row of A2, for example? Either it was a row of AI, because we switched rows, and obviously that's a linear combination, right? Or it was a scalar multiple of a row of AI, which is again a linear combination of the rows of AI, right? Or it was some row of AI plus a scalar multiple of another row of AI, which is again a linear combination of rows of AI. Do you agree? So AI is a linear combination of it, and this is obvious because rows of AI were obtained by elementary row operations. I'm not going to take a new board. Elementary row operations. Good? And now the Halmas gets to sit up here in a very weird space. Is it clear?
What did you mark the notation of B as AN?
Well, I said every AI is a linear combination of the rows of AI minus 1. Well, how is B related to this business? Okay? So I'm calling the sequence A1, A2, all the way up to AN. You can even call A A0. Okay, and now it's a sequence where we secretly know that A is the one you start with and B is the one you end with. And then this really captures all of the steps. Okay? Is it clear? Is it clear that every row operation in a single step is a linear combination of the previous rows? Okay, either interchanging two rows, multiplying a row by a scalar, or adding a scalar multiple of a row to a different row. Do you see that those are all just linear combinations? Good? Clear? Okay, so if you really want to, you're invited, and it's good practice to spell out all the details of this, to write it formally. Okay, so you would need to write everything we said, but in more detail. There's nothing missing here except the details. Okay, the core of the proof is really here. This is a complete outline of the proof. Okay, the other direction is more complicated, and we're not going to do it. Okay, so what I want to do next is define what is a basis, do some examples, then define what is a dimension, and do some examples, and we'll see how everything relates to the things we've been doing so far.